Okay, guys. So let's real quick finish some of the last few things from previous Wednesday's lecture on the basics of optimization problems, and then we have quite a bit to go through today as well. So I may actually go a bit faster, just so we can get through all of it. I think that the slides are pretty self-contained, so if I go a little too fast, then you can always look through those, or you can always come to my office hours or the TA's office hours for help. Mine are today, just to remind everybody, at 3. And also to remind everybody, in case people have forgotten, the first homework is due tomorrow. I think we said it's due at 5:30. Yeah, and it's due in right outside of Christoph's office. It's on the 8th floor of Gates. Okay, so let's just real quick review a couple things that we said last time right at the end. Partial optimization. If you have a convex optimization problem, then you can always partially optimize over some of the variables and get a convex optimization problem out. That was something that we discussed, and the fact that this is convex, given that this is convex, that comes from the property of convex functions, that if you have a convex function, say, in variables x and y, and you optimize out over y in some convex set C, then the function you get out is always convex. That was an operation that we know preserved convexity from our lecture. Okay, so an example of this partial optimization we saw last time was the hinge form of the support vector machines, which I claim is the form that I think is very natural, and I always remember this form rather than the one with slack variables. And what we did is we actually optimized out over these slack variables psi I, and we saw that this is the usual constraint that we have for support vector machines, but we argued from first principles that we actually should have an equality at the solution, because if it was ever strictly larger, then the criterion would be larger than it needed to be. Okay, that was the kind of basic argument that we made. So when it's an equality, we've solved for psi I in a sense, and so we can replace it in the criterion by just the max of 0 in this quantity, which I've written like this. We'll use this notation probably again. This this plus just means the positive part, so it's the max of that thing in 0. Okay, so that's another form of the support vector machine optimization problem, and now there's only the hyperplane variables beta and beta naught. There's no longer the slack variables. The next thing we saw real quick at the end was a transformation and change of variables. We can always transform the criterion by a monotone increasing transformation, and that we won't change the solution. Yes, we will, in general, change the optimal criterion value, but if what we're interested in is the solution, which is kind of what we always seem to be interested in, and which is why I've denoted an equivalence here, then the solutions to those two are the same. Okay, like a real classic example for something we do in statistics is that instead of maximizing the likelihood, we maximize the log likelihood. It's the same principle as what happens here. And we can also transform the variables themselves. So we can transform to, from, say, n-dimensional space to m-dimensional space. We can change x to be phi of y, and now we can optimize over y, as long as phi is a one-to-one transformation, and its image covers the feasible set. So as long as we could express every possible x in this feasible set as some phi of y, then we're OK. And we can now think about the problem in terms of y if we want to. Do I have an example of that here? Let's see. Yeah, I have an example of that coming up. So geometric programming is a good example of transforming the criterion and transforming the optimization variables. It's interesting, but to be honest, I don't really use it at all in my own research, and I don't think it has a big role in statistics and machine learning. So I guess in that sense, I'm biased, and I think it's probably not worth covering because we're also short on time. So it's interesting. You're not going to be tested on it. It's not going to be on the homeworks as far as I can see coming up. So I'm just going to skip over it. But it's an example of a problem that, when written in its original form, is non-convex, but can be transformed into an equivalent convex problem. Okay, and it may help with some of your own research. So if some of these things look familiar to things you're seeing in your own research, you might want to take a look at this. Okay, but the details are on the slides, and I also give you a reference to a nice tutorial on geometric programming. So we're just going to completely skip over that. Okay, so let's talk about an important special case of changing variables, and that's eliminating equality constraints. So oftentimes, equality constraints will be kind of a nuisance in an optimization problem. They may complicate the algorithm, or they may complicate the way in which we think about the problem. So we can actually eliminate them generically as long as they're linear constraints. So as long as the problem is convex. And the way we do so is as follows. We can always think about the set of x's that satisfy the linear system of equations ax equals b as m times y plus x naught. So where y becomes a new variable, and x naught is a single solution to the equation ax equals b. Okay, so x naught satisfies the linear system ax naught equals b. And m, I said here, the columns of m span the null space of A, which means that if I ever wanted to get a vector such that A times that vector was 0, I could just take linear combinations of the columns of m. So in other words, m times y is in the null space of A for all y. That's just saying that last sentence over again, which means that if I were to take A times m times y, then I get 0. Right? That's what it means to be in the null space. So in other words, if I have any x which is equal to my plus x naught, then that is equivalent to ax equals b. Okay, this is true for some y. That's equivalent to ax equals b. Right? This direction, you can just see directly multiply by a, check that a times this x equals b. If you want to ask this direction, well, it's because the columns of m actually span the null space of A. So we can get everything in the null space of A by taking m times y. Okay, so this direction is just invoking some basic facts from linear algebra. So in other words, if we want to think about the problem in a different variable, we can think about it in the variable y. And where we see x, we have to replace it by m times y plus x naught, where x naught was just one solution. And in doing so, we've actually eliminated the equality constraints. You can see this problem, it doesn't have any equality constraints whatsoever. Okay, so this is a completely equivalent problem to the above. Why might we not want to do that in practice? So in principle, this is nice because we can now study this problem, and maybe it's simpler because the equality constraints are gone. Why in practice we may not want to do this? What could possibly be something like bad about that strategy? Any thoughts? Sorry? Yeah, that's one thing. So we need to calculate m, right? Calculating m may be expensive, especially if the optimization variable is very large, or if the number of constraints is very large. So that's certainly, one thing. Something else? Yeah.
Also, that x0, I mean, there might be multiple x0s. So how can we be sure that which one to pick? It's not obvious to me at least.
That's a fair point, but this equivalence holds for any x0, so as long as we find one, we're okay. So as long as you find a solution, you can solve this problem and be assured that at the solution, if you take m times, say, y star plus the x naught you started with, you'd get a solution to the top problem. So as long as we find a solution, x naught to that linear system to begin with, we're okay.
Constraint GI could be very complicated after having my.
Yeah. I guess I'm looking for an answer that's I'm not really leading you to it, so I guess it's kind of hard to answer. But we could be destroying structure in the solution, or sparsity, for example. So let's suppose that x was sparse at the solution, which meant that many of the components of x were going to be 0. Then actually, we'll see later when we talk about coordinate descent or other algorithms even, that such structure makes it easier for us to solve these problems. Our optimization algorithms can actually run more quickly. Here we may have destroyed that. Okay, this y could be dense at the solution. So we may have destroyed some of the structure in the problem. It may actually be slower to solve this one than it was to solve this one. Okay, so sparsity is just one example of structure that may make the problem faster. Yeah?
So that equality for column of m equals to null A wouldn't that be enough only to have subset?
No, I'm actually saying these two problems are equivalent, so we need them to be. Otherwise, we could be outside of the feasible set, right? In the second problem. Oh, if it was a subset, actually, no, then we would not be expressing every x in this feasible set as such a y. So we do need the column space of M to be at least as large as the null space of A. Okay, so that's just an example that we may do that sometimes, and if it's a small problem, then there's probably no hurt in doing that, just to get rid of equality constraints. So now you have at least one transformation that you can maybe just go forward and try whenever you have an equality constraint. Something of kind of, in a way, the opposite direction is to introduce more equality constraints. And that's something we do sometimes to get things in what's called standard form, which we'll talk about today when we talk about, let's say, linear programs. But this trick is about introducing slack variables. So let's consider the following problem. Sometimes we may want to change that inequality constraint on GI to an equality constraint. To change the form of our optimization problem, it's sometimes convenient to express optimization problems in different forms, like we'll see today with linear programs. And we can do that by actually introducing another variable, s. This is a typo. It should say minimize over x and s. S is another optimization variable. And we've replaced the inequality gi of x is less than or equal to 0 with gi of x plus si equals to 0, and si is bigger than or equal to 0. So these two together, you should convince yourself, are equivalent to gi of x being less than or equal to 0. Right, if I have to add something non-negative or positive to gi of x to get 0, and it's equivalent to gi of x being less than or equal to 0. Okay, so these two problems are equivalent. And now we only have these kind of simple inequality constraints, right? Just an optimization variable being bigger than or equal to 0. And we have a bunch of equality constraints. But this bottom one is not convex unless these functions are affine. Okay? Or in other words, according to our general definition of convexity, in order for this to meet our general definition of convexity, we need this to be an affine function. Okay? Because then we'd have something like ai transpose x plus b plus si equals 0, which is affine in the variables x and s. Okay. And yeah.
So regarding the previous page, when we are trying to eliminate the previous page, when we are trying to eliminate the inequality constraints, is there a way just to write ax equal to b and write it in terms of 2 or ax less than or equal to b and then a minus ax less than or equal to b?
Yeah, so you're saying we can turn this into two inequality constraints.
Yes, so we can avoid this situation and preserve sparsity.
That's true. So just to repeat the comment so everyone can hear it, we can always rewrite this as two inequality constraints. That's usually not helpful, though. We're going to see, well, I haven't really told you why we want to eliminate equality constraints, but in some problems, having equality constraints is prohibitive. And when we talk about, for example, interior point methods, which will be a unit about midway through the class, it's going to be kind of, let's just say, cumbersome to have equality constraints. But if we were to change that into two inequality constraints, that doesn't help, because then there's no interior to the feasible region you described. Right? Those two equality constraints are exactly equivalent to an equality constraint. And interior point methods operate on something like the interior of the feasible set. But yours has no interior, so it doesn't really help to make two inequality constraints. Even though it's not a bad idea, it just doesn't help for the problems that we usually want to eliminate equality constraints in. Good question. Okay. So this is another general technique that we sometimes will talk about, which is just relaxing the constraint set. So let's suppose I ask you to solve this problem. Okay, minimize f subject to x being in a set C. And remember that that's a completely general prescription we learned for optimization problems, because this can encapsulate all the constraints that I want. Suppose that I actually take a bigger set than the set C that you asked me to optimize over, and I call it C tilde. And And I actually solved the problem, minimize f of x subject to x being in C tilde. And we often call that a relaxation of the original problem, where the constraint set's been enlarged, right? We've gone from optimizing over C to C tilde, and its optimal value is always going to be smaller than or equal to the optimal value from the original program, right? You can see that because if I asked you to minimize f over this set C, and instead you managed to optimize it over C tilde, then you could have done at least as good, if not better, over C tilde than you could have over C. So an important special case of this is to relax non-affine equality constraints. So if you ever had a problem that was not convex because these equality constraints were actually not affine functions, like if you were the problem you're trying to solve had equality on a bunch of, say, convex functions, then you can change that to a less than or equal to 0, and the criterion value you will see when you solve it is going to be at least as good as what you saw originally, if not lower. Okay, so that's a general kind of relaxation trick you can keep in mind. Sometimes this relaxation actually is tight. So by relaxing this equality to an inequality, you actually retain the same optimal value and the same solution. And sometimes that's the case, like, yeah, I mean, there are many examples that we could go through, but I actually have an example in the slides for which this is a problem in which we have an equality constraint that's not a convex. It's not one allowed in a convex problem because this function, let's say, is not affine. But in the context of this problem, you can convince yourself that by relaxing this to an inequality, well, we know it's convex, but we actually haven't changed the problem. So that happens sometimes. It's more of a case-by-case basis in which you can tell that a relaxation is tight. This one it's fairly interesting, but I think it's just an example of how you might argue that relaxation is tight. I don't think it's a critical problem itself. And it comes from the Boyd and Vandenberg textbook. So if you're curious about it, you can read more about it here, or you can read the textbook. The basic idea is that this b variable is a budget at every time step t. And here we're saying that the budget at time step t plus 1 must be the budget at time step t plus something to do with how much money we got back and how much we invested. Now, if you relax that to an inequality constraint, then I'd be saying the budget at time t plus 1 is at most something like the budget I had at time t plus the difference in my returns on my investments. But at the solution, I'm never going to throw out money. Okay, I'm never going to make my budget smaller than it needs to be. If I have an inequality constraint, you can kind of argue directly, like we did with some of the previous examples, that it's not going to change the solution because throwing out money would never be optimal. This is an investment problem. So in this case, we can see that by relaxing it to an inequality here, we actually have a convex problem whose solution is the same. Okay. All right. I also want to talk about principal component analysis. This thing is, I think, kind of a more fundamental example of where we can relax an inequality constraint and get something that's convex and equivalent. I think it's pretty interesting. So let's suppose you're given a matrix X and it's n by p, and I ask you to find the rank R matrix. So that's, remember the definition of rank let's say for a rectangular matrix means that it has exactly k non-zero singular values. Or, for example, the columns of R span a k-dimensional space. Those are two ways of thinking about rank. Suppose I want to make a low-rank approximation to a given matrix X. Okay, you give me X. I'm trying to find a matrix R that's close to it in terms of squared error, but has rank k. And here I'm using the Frobenius norm on the matrices just to denote the sum of the squares of the elements. So it's like unraveling the matrix into a vector and just taking the squared L2 norm. So this is also called principal components analysis. We're trying to find, it's equivalent to principal components analysis, the low rank matrix approximation problem, and has many applications and uses in machine learning and statistics. And first, let's just note this is not a convex problem. Okay, this is not a convex problem. This is actually a convex function. This is just like taking, quadratic in our optimization variable R. But this is not a convex constraint set. Can somebody tell me why that's the case? Why is rank being equal to k not constraint, not a convex set? The set of all matrices, let's say R, such that rank R equals k is not convex. convex.
Or take A and minus A. Do something else.
Yeah, that's a good example. So suppose I have A, so let's just call this C. Let's suppose A is in C, so it's a rank K matrix. Then certainly minus A is going to be in C. It's also going to be rank K. And if I take, let's say I take half A plus half of minus A. So this is a convex combination of A and minus A, and it's 0. It's the 0 matrix. It's not going to have rank K. So it's certainly not going to be in the set. Okay? You can think of lots of other examples. Like, for example, this is 2 by 2 matrices. This is a rank 1 matrix, and that's a rank 1 matrix. Okay, but their convex combination is going to have rank 2, not rank 1. Okay, if I take half of this plus half of this, for example, it's going to have rank 2. So it's definitely not a convex. I mean, if I'm allowed to have an artist's depiction of this constraint set, it really kind of looks like a bunch of spikes everywhere. It's not, you know, I have matrices kind of shooting off in different directions. It's not a convex set. So nonetheless, we can actually solve this problem. And you know, for those of you who've taken stat and ML courses, you'd recognize this hopefully, which is just take the SVD of X and truncate it. So take the singular valued composition of X, which I write as a UDV transpose, and then just delete all the diagonal elements in D after the kth entry to set them equal to 0. Or you can also think about just take the top k by k block of D, and then take the first k columns of V and the first of U, and take the first k columns of V. Okay, so truncate the SVD, and that thing's going to have rank K by construction, right? And it's actually going to be the closest matrix in the Frobenius norm to X that you can find. So that is the solution, even though it's a non-convex problem. It just so happens that we know the solution. Comes from reconstructing X from its first k, top k singular vectors, and U and V. So we're going to actually learn that we can recast principal components in a convex form. This is something I didn't know about myself until just a few years ago, and I feel like it's not a very well-known fact in both in optimization and in statistics and machine learning. But it's something that's quite an old fact. It's just that people don't really revisit it. So we're going to basically take this problem. This is equivalent to the previous problem. Here I'm saying I want to find the matrix Z, which is symmetric, and it's a projection matrix of rank K. And I'm saying I want to project X, multiply X by Z, which means project it down to a rank K matrix. And I want to find the projection matrix from rank K that makes this as small as possible. Here I've just substituted R for X times Z, where Z is a projection. So these two problems are equivalent. And I have Z having rank K, and Z must be a projection matrix. Okay. Projection matrices, I guess here I write it here. A projection matrix you can think of as having the property that it's a symmetric P by P matrix. It has rank K, and actually all of its eigenvalues are either 0 or 1. It can have eigenvalues that are only 0 or 1, nothing else. That's one way to characterize a projection matrix. And the trace of any matrix is its rank, right? And sorry, the trace of any matrix is the sum of its eigenvalues. And here I told you that its eigenvalues are just 0 or 1. So the trace of our matrix, if it's a rank K projection matrix, should be K, because it's the sum of its eigenvalues. And the sum of its eigenvalues is exactly K, has exactly K eigenvalues that are 1. So this is a way of writing the constraint set. It's a set of all matrices Z that are symmetric. They have eigenvalues equal to 0 or 1, and the trace is K. Not a convex constraint set because of this thing. Okay. And I just rewrote the criterion as a max rather than a min by expanding the square. So it turns out if I just expand the square here, and I get rid of terms that don't depend on Z, I can think about this problem as I want to maximize the trace between X transpose X and Z, subject to Z having rank K and Z being a projection matrix. So all these are just equivalent forms of PCA. We've really done nothing fancy so far. We've just introduced xz for r, and then I expanded the square and got rid of some terms that didn't depend on z. So this is the same problem as before. It's still just as hard because it's non-convex. And to solve this problem, I can just take z to be vk transpose, where these are the right singular vectors, the first k right singular vectors of x. So it's another way of looking at the PCA problem. Now we're gonna learn that we can recast this in a convex form by replacing C with a bigger set that's convex. Okay, C is not a convex constraint set. We're trying to maximize that function, which is actually just a linear function of our optimization variable, right? The max of the trace of S and Z is just a linear function of our optimization variable Z. But we're optimizing it over some very spiky constraint set. This might be C. And we're going to actually replace C by a bigger set that's convex. And what's the smallest set that's convex containing C? It's convex hull. Right, so we're actually going to take C tilde to be the convex hull of C, and we're going to try thinking about solving the problem over this convex hull instead of C itself, and see what that problem looks like. So first, I'm just going to state this, and I don't think it wasn't on your homework, although it would not be a bad idea to try this as an exercise. I claim that the convex hull of this set right here you get by actually just allowing the eigenvalues to be between 0 and 1, inclusive. So the convex hull of this set is a set of all matrices such that they're symmetric, they have trace equal to k, and each eigenvalue is just between 0 and 1. It's in the interval 0, 1. That's the convex hull. And another way of writing that is that, remember we know how to talk about an ordering on matrices using positive semi-definiteness. I can write that as 0 being less than or equal to z being less than or equal to I. Every eigenvalue is between 0 and 1. Was there a question?
What was the v in the previous slide?
This v was it was the right singular vectors of x. Okay, so this problem, if I replace the constraint set by this guy, which is really it's really quite similar to what I drew, but over matrices. It's like a polyhedron over matrices, right? Because here I have a bunch of linear inequality constraints on Z, and that's an equality constraint on Z. So it's like having a polyhedron over matrices. We actually call it a fantope after the inventor, or what do you want to call discoverer of this matrix polyhedron. If we were to minimize our criterion function over this set, that's a convex problem. Because the constraint is Z lying in a convex set by construction. This was the convex hull of projection matrices, so it's convex, and this is linear, right, in Z. So that's actually a convex problem. And remarkably, this is what I think people don't really revisit when we teach PCA or talk about PCA. This is completely equivalent to PCA. Even though that we've actually relaxed the constraint set to go from projection matrices to matrices that are in this set, right, which are bigger, it's like this bigger polyhedron, the solutions to those two problems are exactly the same. It's because this very famous and elegant result from Fan in 1949, he proves that the solutions always have to lie at the extreme points. So even though that we're optimizing over the polyhedron, the solutions are actually going to lie at the extreme points. They're not going to lie somewhere else in the fantope. Okay, so I think it's a pretty interesting result, and it means that the reason I learned this was because people had started working on extensions of PCA to account for things like regularization and sparsity, but moving from this perspective, because now this is a convex formulation of PCA. So if I want to start doing things like penalizing, let's say Z or something, or V for sparsity, then I can go from there, and I have a convex problem as a jumping off point.
When you started out, you put R equal to X times C. How general is that?
I mean, I can always express, if you tell me that you have an n by p matrix of rank k, I can always take your n by p matrix and multiply it by a rank k projection matrix to get that. I can always, that transformation is fully general. Other questions? Yeah.
We know that the rank R equals K constraint is non-convex, but just checking, if I were to change that to at most K, rank R at most K, that would be a convex set, right? Because no.
Same example, right? For example, here are two matrices that have rank 1, and their convex combination has rank 2. Other questions? Yeah.
How does this relate to the other formation of PCA where we think about the back projection being the transpose of the forward projection?
The back projection. Do you mean like the sequential formulation of PCA?
You think about your input data and you project it using some matrix and you make the constraint that to project it back, you just take the transpose of the projection. Like, and you minimize reads.
I think this is the same formulation. So we can always write this as, I can always write, x times z as x times VV transpose. And if you think about the rows of x as the instances, then this is projecting, if I look at this first factor, this is like projecting all of my instances down to a k-dimensional space. This is lifting it back. And so it's the squared error loss between that. Okay, all good questions. I thought this was just an interesting kind of fact about principal components analysis to share, that it's actually equivalent to a convex problem. And I should also, attribute this, the fact that this fact is quite old. It's 1949, so, that's where it came from. But Vince Vu, who used to be in the statistics department, and Jing Li, who's currently in the statistics department, they're the ones who told me about this. And they actually have some nice work where they, for example, they define a sparse principal components estimate by a sparse version of principal components analysis by jumping off from this formulation, which is convex. So by adding things like an L1 norm or other kind of, more standard things, you can have a convex regularized formulation for PCA. Okay. All right. So that was just going to wrap up our last bit. Now let's jump into some. I won't go through the last time because we just did all that. Here's what we're going to talk about in the rest of the time today. So LPs, QPs, STPs, and cone programs. And this is going to try to give you kind of like a view of the hierarchy of convex problems. And then after today, we're going to start talking about some specifics. So this lecture, they're all kind of quite general. They're telling you things about optimization at a very high, it's like 30,000 foot view. This is what the form of a problem is. This is how you change from one form to another. Starting on Wednesday, we're going to get very specific and talk about an algorithm, gradient descent, which is maybe the most basic algorithm you could talk about. And we'll have an algorithms unit that's kind of much more specific. So this is our last kind of general theory of optimization lecture for this unit. So this is the picture I want you to walk away with after this lecture. And it's a picture of the hierarchy that we associate with different types of convex optimization problems. And this is a picture that you will see in various spots. LPs are, in a sense, kind of like the most natural, the simplest convex optimization problems that you can think of, and we're going to define those in just a second. Bigger than that, so which includes LPs as a special case, are QPs, quadratic programs. And quadratic programs contain quite a bit more problems than linear programs do. So for example, quadratic programs, both support vector machines and the lasso are examples of quadratic programs. And so quite a bit of common, quite a number of problems in machine learning and statistics are examples of quadratic problems. Then going from QPs to STPs actually is a huge jump. So that's why I've made this, this so drastic in the picture. STPs are actually like a really, really big problem class, and they contain QPs and LPs and a lot more. So a lot of other things. And if I'm allowed to be kind of a bit non-rigorous, STPs are really hard to solve, whereas QPs and LPs are pretty manageable. So if you give me a QP and an LP and thousands of variables, that's not really a problem anymore. Even CVX or kind of standard commercial packages, they should be able to solve that no problem whatsoever. STPs and a few thousand variables, that can be really, really hard depending on the STP. So even though they're convex, they're just such a big problem class that it's not that easy to describe algorithms that work well kind of over all STPs. Then conic problems are arguably the largest class that we know of for convex problems. So they contain everything that we've described so far. They're huge. The way that software like CVX actually operates is that it transforms everything that you pass it in terms of the DCP language into a conic problem, and then it chooses to solve that in one of various ways. So it's a very large problem class. Like I said, it's arguably the largest that we know of for convex problems. And the same as STPs, it's kind of, I guess it's not really clear how much larger they are than STPs, but they are larger, and it's not really, if you gave me a conic problem and a few thousand variables, that may be very difficult to solve, even though it's convex. Okay, and then I don't think I have another picture. So the last picture I like to draw, just to remind you, is that what we're looking at really is something like this. If we were to zoom out, we have something like this. Convex problems and non-convex problems. So really, it's like a drop in the bucket. I don't mean to be bleak or something or get you depressed, but convex problems are also pretty special. And for every convex problem we know of, we can think of a lot more non-convex problems that exist and that are much harder to solve. So we're really kind of living inside this little bubble for the moment. Okay, so linear programs are an LP. It's the first problem class that we're going to learn. It's a problem in which the criterion and the constraints are all just linear functions. And like all convex problems, it has linear equality constraints. Okay, so minimize C transpose X subject to a bunch of linear inequalities on X, dx less than or equal to, say, a vector D, and a linear equality A times X equals B. So this is the most kind of generic way to express a linear program. And it's always a convex optimization problem, no matter what that matrix D is, no matter what the matrix A is, no matter what these vectors C, D, and B are. It's always a convex optimization problem. That's because this is always convex, and this is always a convex function as well. Okay, so even if we wanted to pass in the weirdest matrix D you could think of, or vectors or whatever, it's still going to be convex. And we can decide to minimize over X. We can also decide to maximize over X. That would also still be convex, because if we wanted to maximize over X, C transpose X subject to the same constraints, it's equivalent to minimizing minus C transpose X. But that's still a convex function, right? It's affine, so it's both convex and concave. So there's a lot of history surrounding linear programs. I put some of it down here. In some disciplines, like in operations research, Javier might tell us a bit more. They actually teach entire courses on linear programming sometimes. So linear programs are so fundamental, and there's actually quite a bit of applications of them, that some people would take an entire course on linear programming and all the various ways to study them and to solve them and LP duality, etc. So there's quite a lot to say about them. We're just going to look at them as kind of one instance of an important instance of a convex problem, and yeah, because our scope is kind of quite a bit broader. So here are some examples of LPs. So this is kind of a fun one. You might call it the diet problem. So X is going to be basically each component of X is the amount of food of that type you're going to include in your diet. So let's suppose there are like 10 different foods you're thinking about eating. So X is going to be 10-dimensional, and Xj is the units of food J that you're going to be consuming as part of your diet. Say, I don't know, per day or something. Think about like how much you're going to, what you want to eat in any one given day. And what you're going to want to do, let's suppose, is to minimize how much money you spend on food. Okay, because you don't want to spend money unnecessarily. So Cj is going to be the per unit cost of food j. So C transpose x is the amount of money you're going to be spending on food per day if this is going to be your diet, if x is dictating your diet. This is, so you want to minimize the cost of how much money you spend each day on food, subject to, well, I can't consume negative amounts of food. That's this thing. X must be bigger than or equal to 0. I can consume, let's say, the least amount of food I can consume of any type is 0. And that constraint, dx bigger than or equal to d, I can rewrite if I want. Let's suppose I call the rows of d, let's suppose I call those dj. Then I'm saying that dj transpose x has to be bigger than or equal to dj for all j. And let's suppose that j here, so the rows of d or the components of this guy, this vector d, they index different nutritional requirements. Like let's suppose calcium is one of them. This is saying that I need at least this much calcium in my diet, otherwise I'm going to get sick. And dij is the amount, I should probably use I. Let me use I so I don't confuse everybody. Let's call it di for all I. So let's suppose I is calcium, and I say that I need at least this much calcium in my diet, and dij is the amount of calcium in food j. So this thing, di transpose x, is the amount of calcium I'll get out of eating these foods that x describes. So these are all the nutritional requirements I must meet. So apparently, although I don't know how much truth to this there is, LPs were solved in the Russian army in some ways to dictate what the people who were in the army ate. There are lots of stories that are interesting about LPs and how they have a history with the army, especially the Russian army, both for transportation and for diet. So this problem apparently has some basis in reality. Another problem is transportation problem. I guess we could go through a similar story, but I might just skip it because I don't know how much value it has. Just as trying to convince you that LPs are actually pretty expressive, and you can express lots of different interesting problems in the LP formulation. Another example of linear programming is basis pursuit. So now we're kind of getting to more towards the stat ML side of things. And it's similar to what we talked about with the lasso, although it's a bit different. So let's suppose that I had a vector y and I had a matrix x, and let's suppose I wanted to predict y from the columns of x. Okay, something that we've talked about a bit with the lasso and in regression. But I actually want to do that in a sparse way. So I want to take only a small number of columns of x when I form that linear combination. And in basis pursuit, which is different than what we do in the lasso, we actually are expecting to find coefficients that make x beta equal y exactly. So we call this kind of like a noiseless case. Suppose we're actually looking to match y exactly rather than just be close to y. In the lasso, we think about having some noise in our measurements, so we'll try to make x beta close to y in squared error. Squared error loss, this is a little bit different. Sometimes call this a noiseless case. So we want to find beta for which x beta is equal to y, and we want to make beta sparse. So the sparse solution, we want to find, let's say, the sparsest solution to an underdetermined system of linear equations, this guy right here. So the non-convex way of doing this is to minimize the number of non-zeros in beta subject to that linear equality constraint. It's non-convex because this is a non-convex function. You can convince yourself that the L0 norm, which I'm just, I guess I'm defining it here, it's the number of non-zeros in beta. So this is going to be 1 when beta is non-zero and 0 otherwise. That's not a convex function. It's really very similar to some of the arguments we gave with rank earlier. It's definitely not convex. We can approximate this guy by the L1 norm. This is one way in which kind of the L1 norm popped up in statistics and machine learning as being a very natural thing, was to think about something like this, then to think about convex relaxations of it, and we can relax this with the sum of the absolute values of beta. So that's called a convex relaxation of the L0 norm into the L1 norm. This is now a convex sorry, a convex problem, because this is a convex function. As we know, all norms are convex. And this is called the basis pursuit problem, the name we attribute to it in statistics and machine learning. And that is actually a linear program. Do I have? Yeah, I have it here. Basis pursuit is actually a linear program. It's an example of a nice LP we might want to solve, because we can actually reformulate it with additional optimization variables. We can define z to be a set of additional optimization variables, and we can replace the sum of the absolute values of beta with the sum of z's. This 1 is the vector of all 1s. So I've replaced the sum of the absolute components of beta with the sum of the components of z's. So there's no more absolute value. And I'm actually going to keep the constraint that x beta must be equal to y, but introduce two more constraints, which is that each component of z must be bigger than or equal to beta, and it must be bigger than or equal to minus beta. Remember, we interpret all of these component-wise when we have inequalities between two vectors. So you should check this makes sense to you, that this problem is actually equivalent to this one. Right here, we're just essentially defining each component of z must be bigger than or equal to the corresponding absolute component of beta. That's another way of thinking about these constraints. But we've written them like this because it demonstrates it's a linear program. Okay, so basis pursuit is a linear program. Okay, another example of a linear program, so continuing in the stat ML kind of line, is the Danzig selector. So it's very similar motivation. We want to find, a linear combination of the variables x that's close to y, but not exactly equal to y. So now this is actually the same problem that, statistically speaking, that the lasso is trying to solve. It's just a different way of solving it. So instead of enforcing the constraint that x beta must be equal to y, like we do here, we just want to have a constraint that says that it has to be close to y. One way of doing that is actually to look at the vector x transpose y minus x beta and look at the largest absolute value of that. That's what the infinity norm penalizes. Remember, the infinity norm is the largest absolute value of its argument. And here we're saying that that has to be less than or equal to lambda. So we rewrite the Danzig selector. It's minimize over all beta subject to, let's suppose I call the columns of x xj. This is another way of writing that for all j equals 1 through p, where here xj is the jth column of x. Okay, so that's another way of writing that optimization problem. And that is also a linear program. Okay, we can make the same transformation for beta by introducing a variable z to get that part to work. How do we transform this into constraints that are okay by linear program standards? Yeah, that's right. Just make it two inequalities. This has to be less than or equal to lambda, has to be bigger than or equal to minus lambda. Those are two linear inequalities. Okay, and each of them is just a linear function of our optimization variables beta. Okay, so that's how we reformulate it as a linear program. Can anybody tell me why this is a good idea to be making this small? What's the motivation for making this small? Right, I could have also, why don't I just do this instead? This is just a statistical aside. It's not super important from the perspective of optimization. I could also ask that this is small, right? This is the ith element of y, and here xi is the ith row of x. So this is just saying that my predictions, this is what I would get from looking at the columns of x and y, they have to be close in absolute value. It's another way of reformulating it as another way of basically casting a problem to try to solve this problem, right? Find a sparse beta for which x beta is close to y in a way that's also an LP. But why did the authors of this, why did the inventors of this program decide to use this instead of this guy? Can anybody guess? Or
It's like adding a weight to different constraints.
right? It's like adding weights to different constraints. What's special about least squares? What are the stationarity conditions? Yeah, sorry. Yeah, that's right. So if we were to take, if we were to look at this problem, the least squares problem, this problem, which has no constraints on beta whatsoever, and we were to set its gradient equal to 0, what would I get? Right, we know that for convex differentiable optimization problems, we have a minimum if and only if the gradient 0, right, with no constraints. So let's take the gradient of this and set it equal to 0. What's the gradient of that? What's the gradient of this function?
Suppose xt beta plus x transpose t.
It's actually this thing. Okay, so this should hopefully be very natural to you guys after you guys shake off the rust from the chain rule and multivariable calculus and all this. This is just like, you know, if this was one-dimensional, it would be very similar, right? It's, I guess I missed the 2, but I'm setting the, you know, it equal to 0 anyways. Okay, so this is just applying the chain rule to this function. Or you could have also expanded this. I could have written this as, you know, x transpose x beta, or I could beta transpose x beta minus, you know, 2x transpose y, and I could have taken transpose beta and taken the derivative that way. So expand this and take the derivative if that wasn't, if you don't like to use the chain rule. But in any case, this should hopefully become very natural to you guys soon to take gradients and stuff of functions like these ones. This is just a quadratic. Anyways, the least squares solution has this as a stationarity condition, which means that at the solution, we should see this being true, right? X transpose y minus x beta should be equal to 0. So for all the statisticians out there, this should, you know, be also very natural. It's saying that the variables have no correlation with the residuals. That's what this is saying. The residual has no correlation with the variables. This is just saying that the correlation of each variable with the residual is small. So it's a very natural extension of what you asked for in least squares. Okay, that was some motivation behind the Danzig selector. But that's not super important for the optimization perspective, just some motivation for why we want to solve this in the first place. Okay, let's talk about standard form. So any LP can be written in standard form, and that's of this form. Basically, it's a problem with all equality constraints and only a very simple inequality constraint, and that's x being bigger than or equal to 0. So I claim that I can take any optimization problem of this form, of this form, and transform it into one that's of this form. Okay, so basically get rid of like arbitrary looking inequality constraints. And that if you want to think about LPs from now on, you can think about that. That can be the form you remember if you happen to like this form. I'll leave this up to you guys to check. The way to check it is actually just to introduce a slack variable right here. So rewrite this as dx plus s equals d, where s is bigger than or equal to 0. Okay, so now your variables are x and s, and you have all equality constraints, and you have an inequality constraint that s is bigger than or equal to 0. So you're almost there, but the only thing that you're short on is that x is not bigger than or equal to 0. Because in standard form, all of the variables must be non-negative, and you have just equality constraints. So then think about how you would make that, transform the problem once again to get it in standard form. Okay? But this is actually a problem in which you will see people define LPs in this form. It's just another way of thinking about LPs. It's called standard form. Okay, let's blaze through QPs, take a break, and then come back and talk about the rest. So once we've talked about LPs, QPs are actually just a very, notationally, they're a very small change on top of LPs. Although we do get out a lot more problems. So notationally, all that we're doing is we're adding a quadratic to the criterion. Okay, that's a quadratic program, is just taking C transpose X like we had before for LPs and adding a quadratic function, 1/2 X transpose QX. Now, all the QPs that we're going to be talking about by default in this class are going to be convex QPs, which means that when I say QP, I actually mean that this Q matrix is going to be positive semi-definite by assumption. Okay, otherwise this problem would not necessarily be convex, right? If X was not positive semi-definite, then we can't say that this function is a convex function. In fact, it's going to be concave if X is negative semi-definite, for example. But as long as X is positive semi-definite, Q is positive semi-definite, then this is going to be a convex criterion. So it's going to be a convex program. And if we were being very careful, we'll call this a convex QP. But I'll usually just say QP, assuming that this is PSD. Okay. So some examples of QPs are portfolio optimization, something that people do a lot over in Tepper. And Javier will have more to say about this. I think he may actually do a case study on portfolio optimization partway through the semester, just to give you some ideas of what people do in that particular problem framework. But this is a common example of a QP. Basically, X is going to be how much we want to invest in each of a bunch of different portfolios, and we have the constraints that let's suppose we're going to be thinking of them as proportions rather than percentages, but things that are proportions. So X has to be non-negative. We have to think about these proportions as being positive. 1 transpose X must be equal to 1. We have to have our proportions adding up to 1. We're going to have to allocate money rather than throw out money. And so those are just very simple constraints, right? Those are fine for QPs. And then the criterion is of this form. We want to maximize mu transpose X minus, forget about this gamma, it's just a constant, X transpose QX, where Q is a covariance matrix of these assets returns, let's say, in the past, the ones that we're thinking about investing in. And this mu is, let's say, the expected value of each asset's returns from past data. Okay, so first of all, let's convince ourselves that this is actually a QP. It is because I could convert this to a min and put a minus sign, in which case I'd have minus mu transpose X plus quadratic. So that's fine. That's what we had before. And why does this make sense? This is kind of saying we want to trade off something that has high expected value with something that has low variance. We don't want our our portfolio to be very volatile, have lots of variance. So it's something that people do quite commonly. SVMs are quadratic programs. We already saw those. You can see that just by writing this as beta transpose beta. Okay, so another example of a quadratic program. The lasso is also a quadratic program. Something I guess I'll leave you to check. You can think about how can I rewrite this as a bunch of linear inequality constraints. And another way to parameterize the lasso problem, which sometimes we call the Lagrange form or penalized form, where we take this constraint on beta and we turn it into a part of the criterion after we multiply it by another Lagrange parameter or tuning parameter. So in this formulation now we would choose lambda rather than choosing S here as a hyperparameter. This is again a quadratic program. So the way to check that is very similar to the way that I told you that the Danzig selector was a linear program. So we're going to want to introduce a variable z to take the role of this guy here. Okay, but all of these can be cast as QPs. I'll leave you to check the details. And any QP can be written in standard form. So just like LPs, I can take any QP and I can write it in this form if I wanted to. And that means that now that you know these are all QPs, if you're in a bind and you didn't have any other way to solve the lasso or support vector machines or any of these things, then one standard QP solver that comes with, say, MATLAB or whatever is the language you're using, then you can always convert these to quadratic problems and just throw that into the QP solver and get answers. Okay, these are all just QPs. So as we can see, QPs are actually quite general. And of course, they include LPs as a special case, just when Q is equal to 0. I guess we never explicitly said that, but QP obviously includes linear programs. All right, any questions? Kind of went through QPs quickly. Let's just take a few minutes break, and then I'll come back and do STPs. Let's put a bit of motivation behind STPs before we get to them. So let's remember linear programming, right, which was a problem that we introduced over vectors that had a linear criterion, linear constraints, inequality constraints, and linear equality constraints. So let's suppose that somebody gave you a matrix. Okay, X was now, instead of being a vector, it was a matrix. And they asked you to define a similar problem in matrix land. The answer would be STPs. So it's really just the matrix version of a linear program, given by changing this less than or equal to a different partial ordering on matrices. Okay, it's a partial ordering because we can't really compare any two matrices according to this curly less than or equal to, but we can at least compare PSD matrices. So right, let's suppose let's introduce first of all a bit of terminology we had before. Remember, this is the space of n by n symmetric matrices. That's what we denote by Sn. And Sn plus is the space of PSD matrices. So I've written it here explicitly. I don't know if I wrote this in slides before, but it's a set of all matrices for which U transpose XU is bigger than or equal to 0 for all U's. Okay, it's one way of defining a PSD matrix. Another way, just to remind you, is that all of its eigenvalues are non-negative. And Sn plus plus is the space of I guess I was saying PSD here. I'm sorry. Yeah, that's right, PSD, positive semi-definite matrices. This is the space of positive definite matrices. So actually, we have a strict inequality here. U transpose XU has to be strictly bigger than 0. Okay, all of its eigenvalues are strictly positive. And we're going to basically just change this less than or equal to, change this on vectors to this guy, curly less than or equal to, on matrices. That's what it's going to bring us from LPs to STPs. And remember that we say that, for example, x is less than or equal to y for matrices x and y if y minus x is positive semi-definite. Okay, that's the way we define that ordering. Okay, I have just some basic facts here about these different spaces. I think I already said all of these. At least I said the last two. X is PSD if and only if its eigenvalues are all non-negative. X is positive definite if and only if its eigenvalues are all positive. And the first one is actually just a fundamental fact about symmetric matrices. Symmetric matrices have all real eigenvalues, okay, rather than complex eigenvalues. Just a basic fact. We can define an inner product over matrices that are symmetric, and this is going to be important because, look, this is an inner product over vectors, C transpose X. We're going to want to replace that by an inner product over matrices. Well, the most natural way to do that would be to take every element of X, multiply it by the corresponding element of Y, and add it up. That's what we get when we take the inner product, the standard Euclidean inner product of two vectors, right? It's every element of, like, say, little x times every element of little y added up. We can try to do the same thing with matrices. That's exactly what this is. You know, if you want to write this out as a sum, you'll see that this is exactly the sum of all xij times yij over all I and j, just the trace of x times y. So we're going to denote that by this solid dot. That's going to be our inner product over matrices. And I've already said this in words and before in previous classes. We can define a partial ordering over symmetric matrices. Given two symmetric matrices x and y, we're going to say that x is larger than or equal to y if and only if x minus y is a PSD matrix. Okay, so this thing, this difference, has all positive eigenvalues, or all non-negative eigenvalues. Okay, and it would be helpful for you to think about how this reduces to, what this reduces to when these matrices are diagonal. I think that'll help just kind of solidify that these are the right definitions. If I had a diagonal matrix, for example, where by diag x I mean I take the entries of a vector x and I put it on the diagonal of my matrix, and I asked whether that's bigger than or equal to a diagonal matrix y, where I took the entries of y and put that on the diagonal, then that's true if and only if x is bigger than or equal to y. Remember, by this we mean that every entry of x is bigger than or equal to every entry of y. So that reduces to the usual ordering that we know about over vectors. You should also check that this inner product reduces to the usual inner product if you had two diagonal matrices. Okay, be another thing that you should check. So okay, equipped with this new kind of notation and maybe a bit of a new way of thinking about things, we can define an SDP, which is just given by taking our form for an LP and replacing. Okay, let me actually jump to this one first. That might be the more natural one. It's just given by taking our standard form for an LP and replacing it by all these new definitions for matrices. So remember, before I had for a standard form for an LP C transpose X, where X was a vector. Now I have a matrix C inner product matrix X. Okay, so that's the analogy. Before I had a vector X being bigger than or equal to 0. Now I have a matrix X being bigger than or equal to 0. And before I had a bunch of linear equalities, which I could write as AI transpose X being bigger than or equal to 0. Before I had linear inequalities of this form, or being equal to BI. Now I can think about the analogy to that is a matrix AI dot X is equal to BI. Okay, so those are the equalities that I'm allowing. So I think it's very easy to remember what an SDP is, as long as you remember what an LP is, and you remember what we mean by dot product and bigger than or equal to for matrices. Okay, so that's standard form for an SDP. And what I skipped over real quick is another form for SDPs. And this is where I think this is something that I think people are often confused about, which is that we can write an SDP either as an optimization of a matrix variable, like we do here. And in that case, we usually use standard form. Or we can write an SDP as an optimization over a vector variable. Okay, and those are actually both fully general. They are equivalent in the sense that any SDP of this form can be written in standard form and vice versa. But they're different in the sense that one uses a matrix variable and one uses a vector variable. So that's where they can be I think there can be a bit of confusion. But I wanted to start with this one since you can kind of jump right at it out of LPs. Now let's learn this one. This is also very natural coming from LPs, just coming at it from a different angle. So remember, in an LP, we can write it as the following. Actually, let me write it as this way. So we had gx is less than or equal to h, let's say. Ax equals b. Okay, I'm going to rewrite this guy as each column of G. Let me call it GI. Times xi less than or equal to h. So this is the sum over columns of G. So GI of G. That's another way of writing this constraint. Right? I'm just rewriting GX in this form. What SDPs do in this form is that they just replace essentially each of these vectors, GI, which is a column, by a matrix. And they replace this right-hand side vector, H, by a matrix. And they replace this ordering by the matrix less than or equal to. Okay, so LPs use this, G1, X1, plus, let's say G n, Xn less than or equal to H, whereas SDPs in this form use this inequality. Well, now these are all matrices. Okay, so that's what I've done here. And we require that these things be symmetric matrices. And we place no requirements on A or C or B like we do in LPs, no requirements. And this is always a convex optimization problem, because if you remember, back when we talked about convex sets, we called this a linear matrix inequality. We proved that was always convex, regardless of what these f's were, as long as they are PSD. Okay, so two different forms for LPs. They turn out to be equivalent. When I in the previous slides I said, oh, you can check that an LP can always be written in standard form, a QP can always be written in standard form. Those are, I think, doable checks. They just require introducing slack variables and playing around with the problem. This is actually fairly difficult to prove that an STP in one form can be written as an STP in another form. So I wouldn't worry if you can't show it, but I'm more than happy to give details in office hours or something if somebody's curious. Okay, examples of STPs. There are tons because they're so general. We don't have much time, so I'm not going to discuss very many interesting examples, but we will come back to them when we talk about interior point methods. This is an example from, it has implications both in information theory and also in theoretical computer science. It's a very beautiful example. Another kind of timely example in that it's a popular problem people solve currently is another kind of low-rank approximation problem, similar in some sense to the PCA problem that we discussed, where we replace the rank, which is a very non-convex function, in a system of linear equalities over matrices to the trace norm. And it turns out that actually, well, first of all, we know this guy is convex because the trace norm is a convex function. It's just a norm over the matrix. Remember, it's the sum of the singular values. It turns out this is actually an STP. This is also something that's not easy to show and requires duality. So we'll come back to that later. But I just wanted to give you a flavor of different problems that are STPs. And OK, to finish this off, we have about 5 minutes. I want to introduce conic problems and then kind of complete that hierarchy that I showed you pictorially at the start. So a conic problem is an optimization problem of the following form. So we saw a bunch of different problems. This is problem forms. This one is the most general. So a conic problem is an optimization problem that has a linear criterion, linear equality constraints, and it has something like a linear function of our variable, dx plus d, being in a cone. Okay, that is the form that we think about for conic problems. This K should be a closed convex cone. If I have a problem of this form, we call it a conic problem. Okay, so let's pause for a second and think about how general this is. First of all, I guess I should have said, although I didn't quite say, STPs incorporate LPs. Right? If I have an STP solver, then I can always solve an LP with it because it's a strictly more general form. To see that, you can actually start with standard form, and you can think about what this looks like for diagonal matrices, and that'll tell you that I can get standard form LPs out of it. Or I can also think about this form. Okay, I can think about this form and think about if I had an LP that I wanted to solve, how could I write it in this form as an STP? Okay, so STPs are more general than LPs. Conic problems, it turns out, are more general than both of them. And to see that, let's pause and stop for a moment. For LPs, I can actually take this K to be the non-negative orthant. And if dx plus d is in the non-negative orthant, so if dx plus d is in Rn plus, that means that dx plus d is bigger than or equal to 0 in each component, and I get back LPs. That's just the constraint that I put in LPs, right? So that's how I get an LP out of this, by taking K to be this set. If I take K to be this set, the PSD cone, then I'm saying that then I basically get back this form of STPs. Okay, I precisely get back this form of STPs. So that is a linear combination of my variables being in the, I can write this linear combination of my variables being in the PSD cone just by rearranging this inequality, bringing this over to this side. Okay, so conic problems encapsulate both LPs and STPs. And they are by far the most general problem that we, well, I shouldn't say definitively, but as far as I can tell, they're the most general problem that we can formulate that's a convex one that we can also kind of solve in an efficient way. So the only thing we haven't kind of included so far in the hierarchy, our picture looks like this, right? Our picture looks like LPs, STPs, and conic problems. So we've shown that LPs are a special case of STPs, and they're both special cases of conic problems from this slide. But we haven't talked about QPs yet. I mean, we've defined them, but we don't really know where they lie. For example, it's not obvious that a quadratic problem is a special case of an STP. That's not obvious just from the definitions. And to see that, we need to introduce something called the second order cone problem. So let's see if I can just use the last minute to fit in QPs right here. QPs are going to fit in right there. So a second order cone problem is one of this form. It's one in which I have the L2 norm of a bunch of a linear function optimization variable being less than or equal to another linear function. That's called a second order cone problem. And you can check this is indeed a cone problem by recalling the second order cone. Okay, this was a special convex cone that we discussed. If you think about using that in this definition for K, or really a product of those, Cartesian product of those, you'll get back this optimization problem here. Okay, so it is indeed a conic optimization problem. And it turns out that actually every second order cone problem is an STP. Okay, so second order cone problems actually sit right here. That is not, that fact is not going to be crucial to you from now on. I think it's just helpful to know. But it's kind of a neat little proof. It's very short. You can just go through this if you're curious. We can rewrite this constraint, it turns out, as just a positive semi-definite expression. And that tells us that every second order cone problem is an STP. Finally, we can introduce QPs because it's actually very easy to express any QP as an SOCP. So in order to prove that QPs fall in the hierarchy, we had to first show that QPs were a second order cone problem, and then second order cone problems were actually indeed STPs. So that's how we make QPs fit in. And I think it's a very elegant way of looking at things because it would be very difficult to show directly that QPs are STPs, or it's certainly much harder than this, which is just a couple pages. So let's just finish on that. So a QP I can write as C transpose X plus T, where I've introduced another optimization variable T. And I add the constraint that 1/2 X transpose QX is less than or equal to T. So all I've done is I've added a variable T, and I've moved down part of my criterion down to the constraints. But clearly this is the same problem, right? It's equivalent to having 1/2 transpose X 1/2 X transpose QX in the criterion. And now all we have to do is introduce a variable W to be Q to the half times X, and this is immediately an SOCP, right? Because if I write this inequality in this form, okay, if I write this inequality in this form, I guess I needed a half. Then I can very easily get to an SOCP from this QP formulation. Actually, probably it's easier if I just wrote it out for you. I'm just going to write this as the L2 norm of W is less than or equal to T. I guess a half. This is L2 norm squared less than or equal to L2 norm of W squared less than or equal to T. I'm actually, oh. Does somebody see how I'm missing one step here to think about how this translates to an SOCP? Okay, I don't want to keep you too much longer. Maybe at the very start of the next lecture, I'll just work out the step for you that shows that this SOCP is indeed this QP is indeed an SOCP. Somehow I've temporarily stumped myself, but this is the picture you should recall. This is our hierarchy, and actually it's one layer I've added, which is SOCPs. See you guys on Wednesday.